So when you're looking at chemical equilibrium strictly, what you have are rate constants, one describing how fast things are moving on a per capita basis in one direction, and the other describing how fast things are moving in the other direction. I've drawn these arrows, a big one and a small one, to say that the propensity is to move much faster from B to A than from A to B, but that's on a per capita basis. So for any one B that's out there, its likelihood of turning into A is high. For any A out there, its likelihood of turning to B is actually relatively low. So when you've got a rate going from one thing to another thing that's high, but the reverse reaction is low, what's going to happen? You're going to accumulate the thing that that there's a higher potential to be to accumulate, to be turned into. So B is turning into A and A is accumulating. But there's some potential for A to turn into B, and once you have enough A around on a per capita basis, even though the likelihood of A turning into B is low, you reach a point where, in fact, you're having the production of B equal the production of A. Because you have so much A around that even though A is pretty pathetic at turning into B, you've got lots still that's turning into B. And so at this point where you have this balance in not necessarily the rate at which on a per capita basis something turns into something else, but the overall reaction, as fast as A is turning into B, B is turning into A, are equal, that's chemical equilibrium. And I draw it this way, first of all, to make you realize that you don't have to think of everything as being the forward reaction. Reverse reactions can be important too. But also to give you this idea that at the point of equilibrium, it doesn't mean that the concentration of A and B are the same. It doesn't mean the size of this letter and that letter are equal. It really depends on the rate constants. If A is more stable than B, you're going to have a lot more A, but if you've got a reverse reaction going on, you're still going to have some B, and everything's going to work itself out until you reach a point where you have enough A that the rate at which the reaction is going in this direction is equal to the rate it's going in that direction. That's chemical equilibrium.